Okay, let's go ahead and get started. Let me start with a couple administrative announcements. None of these should be a surprise. There's a problem set 4 is due today. It looks as though most of you have turned it in already. If you haven't, make sure you do so before you leave. There's a midterm this Thursday. I think I've already said what I need to about that, but I'll say it again just in case. First of all, it'll be an 80-minute exam. The format will resemble the format you've seen in the problem sets. It'll be an open book, open note, closed mouth exam. And let's see what else. So you can bring whatever materials you want. You can bring copies of lecture notes, whether they're mine or yours. You can bring your textbook, although I'm not sure I'd recommend that. All those materials are fine. It might be useful to have a calculator. You may use Blue Books, but you don't have to. If you don't use a Blue Book, make sure you get your things stapled so that when pages get lost, there's not a problem. And what else? Other questions about the exam? Yeah. Oh, it'll be. No, you'll need to provide your own paper writing. A Blue Book is fine. If you don't have a Blue Book, it's okay with me. Just make sure we don't lose pages. Other questions? Yes. I'm sorry. Say again. Can you bring a laptop? I would. Let's see. I think it would be a mistake to use a laptop. I'm not sure I'll forbid it, but why did you want to use one? I see. Pardon? Oh, I see. Yes, it's fairly not to. That's right, to print out all the paper. I would discourage you from bringing a laptop. There's too many. Things can happen too, and so it's harder to screw up a sheet of papers than it is to drop a laptop. Yes. The problem sets are all available on DSpace. Oh, I see. If you have a problem set that's been graded, you haven't gotten it back, you should speak to Jeff Barrows, who's will be here shortly. I don't know if he has them with him or not. He may. Okay. Other questions? The best way to study is probably by reviewing the problem set, and in particular problem set 5. And that's what I have to say about the midterm, unless there are other questions. Yes. Oh, I think that's probably placing too great a demand on the GSIs. They're pretty fast at grading, but that's tough. They have midterms now too. So. Yes. So we're not generally posting solutions to problem sets at all. What we're encouraging you to do is ask questions about the problem sets in discussion or in office hours, and we're happy. I mean, the main thing we'd like to be doing during those discussion periods is working through the problems in the problem set. But as a matter of policy, we don't generally post solutions to the problem sets. Yeah. All right, other questions? All right. I want to take a moment to give a shout-out to this gentleman. This is Tom Sargent. He won the Nobel Prize yesterday. Tom, I'm particularly excited about this prize because Tom was one of my advisors when I did my PhD at Chicago. And so he was a very large influence on me. Tom is not a microeconomist. He's one of the best-known and most influential macroeconomists, American macroeconomists of this recent decade. He's one of the people responsible for the so-called irrational expectations revolution in macroeconomics. The sort of issues that concerned him in that revolution, and have concerned him since, have been issues about how consumers behave when something like a price is going to change, but it isn't going to change yet. Instead, consumers know that it's going to change in the future. So he's a macroeconomist, but when we think about natural resource problems in particular, the sort of models that Tom Sargent worked on are very useful for us because it lets us think about how consumers will respond today to an anticipation of, say, higher oil prices, for example, in the future. He's also really responsible for making a lot of macroeconomics rigorous, and this quote is from an interview he gave last year, but it's about the importance of mathematics and economics. So he says here, a rule of thumb is more dynamic, uncertain, and ambiguous as the economic environment you want to model, the more you're going to have to roll up your sleeves and use some math. That's life. Tom was also, something that might make it sort of interesting for you, Tom was an undergraduate here at Berkeley. I think he's more proud of his degree from Berkeley than his undergraduate degree from Berkeley than he is his PhD from Harvard. He's a big Cal fan. Anyway, so there we go. Okay, so I want to spend today doing some review. Thanks very much, Jeff. Some review in preparation for the midterm. I have some material I'm going to work through. I'd also really like to encourage you to ask questions, either as we go along, or questions related to the problem sets, or other stuff that comes up. So if you have questions in particular about topics on problem set 5 or earlier problem sets, today would be a great time to ask those questions. Okay, so I have a little bit of an outline here that I'd like you to sort of think about. None of this material is even remotely new, but maybe it's structured a little bit differently than we've seen before. So I posed this in terms of some questions. So we've been working on a set of techniques now for several weeks that allow us to think about how consumers are affected by changes in prices or changes in income. And we're interested right now in changes in prices in particular. So let's think about a case where the consumer faces a bunch of decisions about stuff to consume, and the price of one of those goods changes. Okay, so we can ask some questions about what the consequences of that are. One immediate question we can ask is, how does demand for the good change? So if the price of the good goes up, what can we say? What do we predict about demand for that good? We've talked about a couple different ways to answer that question. So if the price change, what happens to demand? One of the answers we've got, we can put in terms of the complete answer if we can get it, is if we have a Marshallian demand function or can derive it for that consumer, then we can use that Marshallian demand function to answer the question. So for example, if we have a case where we have a utility function that depends on x1 and x2, and it's equal to this familiar looking object, log of alpha log x1 plus 1 minus alpha log x2, who can tell me off the top of their head what the Marshallian demand function is? Okay, so x1 will be equal to alpha, this expenditure share associated with this good, times the income for the consumer, divided by the price for the first good, which we'll write P1. So if there is a change in price, this formula tells us how demand for good 1 will respond. We can also draw a picture of it. The picture will look something like this. I'm sorry, I want to do the Marshallian demand space here. So we'll put quantity x1 here, and the price of the good here. The demand curve has the form of a rectangular hyperbola as a function of prices. If alpha, depending on alpha, this thing will be a larger or smaller value, depending on y. Similarly, that'll move this thing around. But holding alpha and y fixed, we can think about a change in price from, let's say, p to p prime. That'll result in this change in x1. And in this case, that'll just be equal to something like alpha y 1 over p prime minus 1 over p. So all I've done is, maybe I should not skip a line. So delta x1 is going to be equal to alpha y over p prime minus alpha y over p, and that's equal to this. I just factored out the alpha and the y. Okay, so that's straightforward. You guys can all do that, I think. Any questions about this? Okay, we've got another sort of shortcut. So this, if you know the utility function, so you can derive the Marshallian demand function, this is a great way to analyze the change in demand that goes along with change in price. Another sort of shortcut or something that's useful sometimes if you don't really know the utility function, but you know something about demand. An alternative way to get at this kind of thing is the Slutsky equation. So recall that the Slutsky equation tells us that dx1 dp1. So this tells us how demand changes when prices changes for at least a small change in price. This is sort of local. It's just true at a point. Anyway, this is equal to the Hicksian demand, which is the change in that thing with respect to the price, minus something to do with the angle curve for a good one. So the slope of the angle curve times the quantity of resources spent on that good. Okay, so this is another thing we can use to work out dx1 dp1, how demand will change in response to a price change. Again, for a small change in price. Sometimes we're in a position where we have estimates of this and estimates of this, so we can use this thing. We may not know what the underlying demand function is. We may be able to estimate these quantities from data, so this is useful to use in that circumstance. Okay. All right, so that's a couple different ways that we've worked with that allow us to address the issue of how a change in price will affect demand for a good. Okay. Questions? Yes. Yeah. So the observation is that you've got a partial derivative here. So why couldn't you integrate this back to get the full demand function? And the answer is if you know what dxi dpi is for all values of pi, that's fine. The thing I said about data is often what we observe are some price quantity pairs. So we'll observe a little bit of variation in price, and a few points around here. So we know something about just the local properties, know about sort of the local properties of the demand curve from here, and we may not have a very good idea of whether this demand curve comes from does that or does this, and obviously integrals of those might be quite different. If we have enough data on prices, like a lot of variations, we observe a lot of quantity outcomes for a wide variety of prices, then doing the integration scheme you have in mind might work. But in a lot of applications, we see relatively small variations in price, and so we're left being able to say sort of local things about how demand will change. Okay, other questions? Chris asks, since we're integrating, it's also going to be a constant term here, isn't there? And that's also true. If we had a utility function that was involved one of these fees, for example. So if we had one of these, for example, that would suggest a constant term that would show up in here as well, and we wouldn't be able to figure out what that constant term was just from integrating this. We could by observing levels of prices once we got the thing out. We have other restrictions we can use. Okay. Other questions about that? Okay. So we used this sort of setup last week in an application when I talked about the effect of LED lighting on demand for lighting energy. So it might be worth just sort of plugging in some numbers for that example and seeing what happens. So let me remind you about that setup. So you'll recall, I hope, that we had a few things here. We had, first of all, a commodity space, which is defined over light and other goods. So I was calling those L and Z. So this is light, and Z is other goods. We assumed that the utility function for a consumer could be written like this. We said that we could write it in this nice form, alpha log L plus 1 minus alpha log Z. Actually, we did assume it for the exercise. One of the nice things about what we saw last week was some evidence that supported the assumption that this utility function would work in the form of a claim that income elasticities were unitary for light demand. Anyway, what else do we have? We're going to let the price of light, we'll call that P initially, and the price of other goods, we'll just let it equal to 1. Okay. What else? Oh, we've got a value for alpha. The same exercise that allowed the authors of this paper on LEDs to assert that utility took this form also allowed them to estimate alpha. They got an estimate of alpha equal to 0.0072. So again, it's going to be interpreted as budget share. So 0.72% of the consumer's budget is spent on light. And the interesting thing is that they observe that's fairly constant across both time and different countries. Okay. What else? Oh, this is kind of interesting. So I want to say something about Y in this example. So when I talked about this problem last time, we plugged in an estimate of global GDP in 2010, and asserted that was equal to $60 trillion roughly, I think. I'm going to transform this today to talk about an average consumer instead of the aggregate of all consumers around the globe. And so I'm going to want to let Y be equal to that same figure of 60 trillion, which is, that's 6 times 10 to the 13th. So this is global GDP. I'm going to divide by the world population, which is just about exactly 7 billion right now, or 7 times 10 to the 9th. So that works out, I think, to approximately 85.71 as an average per capita income for the average consumer in the world. There's obviously a lot of inequality in that. There's a very large number of consumers whose GDP is well under $1,000 per year, but there's also a few billionaires kicking around to bring the average up. Okay. Questions so far? Sort of the assumptions for this example. Okay, so we can think about the average consumer in the world having a per capita income, having an income of 85.71, facing the price of light P, price of other goods we're going to assume is 1. We have this utility function. We want to think now about how the demand for the individual consumer will change when we face a change in price. That's what I should say also. It starts off at being $9, and then after it becomes $0.44. So the idea is that currently, using current incandescent technology, it costs $9 per megalumen hour. And with LED technology, it'll cost about $0.44 per megalumen hour. Okay, is that all clear? All right, so how does demand change? So how do we get the change in demand from this? We just want to follow the sort of recipe that I gave up there. So we'll have, let's see, where's the formula? So I have it, let's look at the one I wrote there, alpha y times 1 over p prime and so on. So the change in demand here is equal to alpha times y. I'm just going to rewrite this. 1 over p prime, so this will be the new price, minus 1 over p. And so the change in demand for light here is going to be, in this case, equal to 0.07072, that's the alpha, times 8571, that's the per capita income, times 1 over 0.44, these are the new prices, minus 1 over 9, those are the old prices, and then plugging this into our calculators. Oh, who has a calculator? Let's do this piece. Let's do this in 2 steps, actually. What's this part equal to? This will tell us the average amount of money a consumer spends on light right now. So 0.072 times 8571? Okay, that's $1.61.71. Okay, so we can interpret that as the average amount of money that a consumer now spends on light per year. So that's good. And then this thing is, I think this is approximately equal to, help me out here. So this is, what's 1 over 0.44? Okay, 2.27, and 1 over 9. I should know that one. Yeah. Sorry, point. It repeats, and so this is all approximately equal to, help me out here again. The whole thing? No. Oh, yeah. Sure. And so I'm sorry, what's the bottom line? Yeah, no, it needs this twice 61 plus a little bit. There we go. 133, yeah. Okay, and so this is in the unit that light is priced. The dollars cancel. So this is 133.4 megalumen hours per consumer. Okay, so this tells us that when we get a reduction in price, this roughly 20-fold decrease, we get an increase in total consumption of 133.4. Okay, is that all clear? That's just calculation using this formula. All right. Okay, so another question we can ask, and I'm going to sort of change the second question here, which is how are consumers helped or harmed by the change in price? Yes. Mm-hmm. Oh yeah, that's true. Yeah, I can't remember how that one's posed exactly. So this is very similar to that one, but it's not exactly the same. So you're responsible for figuring out the difference. Yeah.
Now, does this represent like the same amount of lumens versus using like if prices change or just more panel ages, or is this the changing thing?
This is the change. So it's a good question. So Eric asks, is this how much more they could afford, or is it how much more they demand? And the answer is how much more they demand. What's happening? Let me draw a picture for you. So we've got a bigger picture for you. Actually, this one will do. So we've got a demand function that looks something like this, or I'll use this one. We've got a change in price, except the price falls. So we get an increase in demand from here to here. Now, what we just computed is this quantity, is this delta x1. The question of how much more they could afford given that change in price is a different one. That's one where we start off. If they start off here and we've got that suggests that they have a budget line or something like this, indicated to this point in a straight line. If prices change so that we now have a tendency, so that now we are over on this thing, that says that the amount they could afford is going to drop in this price. The amount they could afford is going to be a lot bigger. Actually, I should draw this on this curve, light and z. So here's an indifference curve now. Yes, I'm sorry. Ignore this. I'm confusing my graphs. Pardon me. So we start off with a budget set that looks like this. That pins down light and other goods. Then we get a reduction in the price of L, but hold the cost of Z fixed. So what happens to the budget set? Well, does it just y is constant? What do you mean by shifts? The price of what's the point of intersection? That's y divided by the price of light. And so if the price of light goes down, this thing shifts out. In this case, it's shifting out. The slope is changing by a factor of 20. So we're going to get a really, very flat slope. And so we get this kind of change. So they could afford, a lot more Z if they chose to consume the same amount of light. In fact, what they'll do with this kind of change is shift up. So they're consuming more light, but also, the way I drew it, I guess they're consuming less other goods. But anyway, they'll choose a new point in this indifference curve. And at the old prices, we can figure out, at the new prices, we can figure out what the difference in the budget sets would have to be in order to make these things match up. So that's what I want to do next, which is to figure out what the value of this price change is to consumers. And the way I'm going to answer the question is this. If we gave consumers an option between living in a world where prices were 0.44 cents versus instead of $9 per megalumen hour, how much income would we have to give them at the new prices, or how much income would we have to take away from them at the new prices to make them as well off as they were before the price change? So that's the question I want to ask now. And we talked last week about this measure of welfare. It's called compensating variation. And it's equal to this. It's equal to the expenditure function evaluated at the new price, that's P prime, holding fixed some level of utility U, minus the expenditure function evaluated at the old price, same level of utility U. Okay, so that's the compensating variation. So if we thought about, if we ask the question, how much better does this reduction in the price of light make consumers, one way of answering it, it's not the only way, but one convenient way to answer this is, well, how much money would you have to offer them or take away from them so that they were just as well off under the new prices as they were under the old prices? And let me try to redraw this picture here. This has a graphical interpretation where we have L and Z. We've got an indifference curve. We're going to hold fixed that offers some level of utility U. There's some initial price of light that yields demands like this and this level of utility. We reduce the price, so we get this new demand function.